G'day everyone, my name is Nick Wright. I work for the Department of Primary Industries and Regional Development, and I'm also doing a PhD at UWA. Today I'm going to be speaking on training sensor agnostic deep learning models for all remote sensing. As you're probably all aware, deep learning models for remote sensing are pretty amazing. But there's some pretty stark limitations to a lot of the models and data sets that are out there. The models are generally trained with a single data set source, meaning they only work well with data that sort of looks like that from the same sensor at the same spatial resolution and at the same processing level. So you end up with very specific models, and this can be really annoying. So for instance, if you're working in the Microsoft Planetary Computer, you'll pull down some Sentinel-2 data, and then you're like, oh, I need a cloud mask for it, and then you realize none of the cloud masks available on Planetary Computer are particularly good. So you're like, okay, cool, no worries, I'll chuck in a deep learning model to do this for me, and then you realize that all the deep learning models only work with level 1 processing data, and Planetary Computer only offers level 2 Sentinel data. So I guess I can't really use this. There's 3 problems here. The spectral bands available for Landsat aren't all available in Sentinel-2. So if you train a model up on Landsat data, you just don't have the right bands for Sentinel to make that work. You've also got the spatial problem. So these models are using convolutional neural networks. So the texture is really important, and the texture of objects at 30 meters is not the same as the texture that you see at 10 meters res. So if you train a model up at 30 meters, it just doesn't know what to do with the 10 meter data. And then even if you've got the right bands and the right spectral resolution, if it's not the right processing level that the model was trained on, the data values are just completely wrong, so the model also doesn't know what to do. So you can fix the spectral problem by, start off by just using common bands. Quite often you don't need to train your model on all the bands available from that particular data set. So for instance, if you're training a model on Sentinel-2 data, you probably don't need the lower resolution bands. You can probably get away with just using RGB and near-infrared. And if you can do that, then you can apply your model to heaps of other sensors. Also, to solve the processing level differences and the spectral responses differences between different satellites, it's a bit of a challenge. So what we have here is a Sentinel-2 level 1 chunk of imagery, the same scene from Landsat with both level 1 and level 2 from the same day. And you can see the first row of histograms, the values are just completely different, even though the images kind of look the same. We need some way of normalizing those to a standard representation, and you can effectively do that in QGIS. If you just zoom into an area and just say, give me a local histogram stretch, it'll just make it look the same, so it'll just stretch it out so you can see all the features in it. You can just do the same thing. So before passing any images into a deep learning model, you can just apply effectively a local histogram stretch or dynamic z-score normalization, and it just standardizes that representation, and you just do the same thing at inference, and then that totally removes the spectral response differences between satellites. And then to solve the spatial resolution issue, or the spatial differences between sensors, you can just have an augmentation in your training pipeline that dynamically resizes the spatial dimensions of a batch before it gets passed to the model. So you can have a Sentinel input that's at 10 meters and just have an augmentation that just squishes that down or stretches it up. So you can represent a whole bunch of different resolutions. You could probably squeeze a bit more out of this too by doing a bit of super res in there, so you can pretend that you've got 2.5 meter resolution imagery, but that's as of yet untested. Next paper. And then, so we've actually done all of this, and it turns out it works really well. So we published a model a couple of months ago called Omni Cloud Mask, trained on just Sentinel-2 data. It achieves state-of-the-art cloud and cloud shadow accuracy on Sentinel-2 for both level 1 and level 2, Landsat 8, PlanetScope, and it works really well with Maxar as well. That's available. You can just go ahead and pip install it. It's also on our GitHub. Totally available, really performant. You can do inference on a Sentinel-2 scene in 2 seconds, running it at 20 meters resolution. It's also one of the big advantages here is because you've trained a model to understand different resolutions, you can make a bit of a trade-off at inference time, so you can trade resolution for speed. So you can run a Sentinel-2 scene through at 10 meters and it takes 8 seconds, or you can run it through at 20 meters and you'll lose a tiny bit of accuracy, but it only takes 2 seconds. Awesome, thank you.